All right. So well, you have already seen a simple rectifier circuit. We can use a diode, just a single diode, to form a very simple rectifier circuit. Suppose I have an AC source. Okay, I have some AC source, and if I connect it to a diode circuit like this, and then connect the signal to a load. Okay, then this works like a rectifier. How does this work as a rectifier? You might already know that, because the input wave to this circuit, the input voltage to this circuit is of the form like this. Okay, I have some input. So this input is a fluctuating voltage source. Okay, mind you, what is the graph I am drawing? I am drawing the graph of voltage. This is the voltage V. I am drawing the graph of voltage versus time. Okay, this is called a waveform graph. Waveform graph. Okay, all right. So this voltage source will be, this is a fluctuating voltage source. All right, sometimes this terminal is more positive, this terminal is more positive than this terminal, sometimes this terminal is more positive than this terminal. Okay, so it fluctuates. All right, so when this terminal is more positive than the lower terminal, then the voltage source will try to supply current in this direction. Okay, this is the direction of the current. Does this diode allow the voltage source to pass current in this direction? Well, it does. As you might already know that if I draw a diode like this, a diode passes current in this direction. Okay, a diode allows current in this direction, but it does not allow current in this direction. Okay, so the diode will allow the current to pass. The diode will allow the current to pass, and it will go through the resistor. Okay, so suppose this is an ideal diode. So when an ideal diode passes current through it, it acts as a short circuit. Okay, so I can draw this circuit like this. I can draw this circuit like this. I replace the diode with a short circuit. Let me make that a bit more explicit. Okay, and I have my load. All right. Now, when this terminal is more positive than this terminal, okay, when this is more positive, what happens? Then this input voltage source tries to supply current in the opposite direction, in this direction. Okay, so if current tries to flow in this direction, okay, let me use another color. If current tries to flow in this direction, all right, it tries to go in this direction and tries to go to the resistor in this direction and tries to go to the diode in this direction. Okay, so will the diode allow this current to pass? Well, it will not, because the diode only, as we saw here, the diode only passes current in one direction. So when the input voltage source is in the negative cycle, the diode will turn off, and an off diode we can replace that by using a open circuit. All right, so I can draw the graph like this. This is an open circuit, and I have my load resistance. Okay, so in the positive cycle, the diode acts as a short circuit and it allows the voltage to pass and current to pass. In the negative cycle, the diode acts as an open circuit. Okay, let me write this. In the negative cycle, the diode acts as an open circuit and it allows no voltage or current to pass. Okay, all right, so let's see. In the positive cycle, in the positive cycle, what is the output voltage if I consider this as an ideal diode? Okay, this is the output voltage. I will take the output across the load resistance. Okay, this is V out. What is the output voltage? Well, you see, if this is a short circuit, then this voltage is equal to this voltage, right? Because these two nodes are directly connected. Similarly, the bottom node is also directly connected. So the input voltage is equal to the output voltage in the positive cycle. What about in the, so I can write like this, in the positive cycle, the input voltage is equal to the output voltage. Okay. And what about the negative cycle? Well, you see, since this point is disconnected, since this point is not connected, in the negative cycle, the input voltage cannot pass to the output. Okay, it cannot pass to the output. So, in the negative cycle, the output voltage, this is the output voltage of the negative cycle. This is, okay, this is V out. So, the output voltage is V out equals 0. Okay. So, if we plot this relationship, we can draw a graph. Alright, we can draw a graph like this, where the x-axis is the input to the circuit, input voltage to the circuit, and the y-axis is the output voltage to the circuit. And well, what will be the relation? You see here, in the positive cycle, means when V in is greater than 0, V output, the output voltage is equal to the input voltage. So this will be a straight line. Okay, this will be a straight line through the origin. And the slope of this straight line will be equal to 1. And in the negative cycle, when V in is less than 0, the output voltage will be 0. Okay. Alright, so this type of graphs in which we plot the output voltage of a circuit against the input voltage. We call these type of graphs transfer characteristics. Alright, these are called transfer characteristics. Okay, so maybe I need to say something clearly that in this course you will be learning about 3 types of graphs. Alright, we will be learning about 3 types of graphs. The first graph that you learned was the IV graphs. Okay, the IV graphs are IV characteristics. We draw the IV characteristics of a device. Okay, IV characteristics only exists for devices, for specific devices. That can be a 2-terminal device or a 3-terminal device. We draw IV characteristics for graph. What is an IV characteristics? An IV characteristics is the graph of the current of a device. That current I can write like ID versus the voltage of the device, VD. Okay. Another type of graph is the waveform graphs. Okay, waveform graphs. Okay, let me write one thing. This is ID versus VD. Okay, waveform graphs are some quantity, some current or some voltage versus time. Okay, an example of the waveform graph is the graph of the AC signal that we saw before. Alright, so this type of graphs, there's some quantity, some voltage or current that we plot against time is called a waveform graph. And the third type of graph that we will be using is called the transfer characteristics. Okay, transfer characteristics. The transfer characteristics only exists for circuits. Okay, we had IV characteristics for devices and transfer characteristics exist for circuits. Okay, specifically 2-port circuits. Maybe I should write that too. This is 2-port circuits. What do I mean by 2-port circuits? I have some circuit and that circuit contains an input port. All right, I can input some voltage or some current to that circuit. Okay, this is the input port, and I can take some voltage or some current from the output of that circuit. Okay, so transfer characteristics is some input quantity versus some output quantity. Okay, some input, sorry, maybe, oops, I have written it in the opposite order. In the y-axis we will have the output, and in the x-axis we will have the input. Okay, I have to write it like this: some output quantity versus some input quantity. Okay, out versus in, and this one will be some quantity. This can be either a voltage or a current versus time. This output quantity can be some V out or some I out. This input quantity can be some V in or I in. Okay, if we plot V out versus V in, I mean in the y-axis you have an output voltage and in the x-axis you also have an input voltage. This is called a voltage transfer characteristics. Okay, voltage transfer characteristics. If you plot some output current versus some input current, then this is called a current transfer characteristics. Okay, current transfer characteristics. Well, in short, we also call it VTC, and we call the current transfer characteristics CTC. And we may also have a mixture of these two, V out versus I in or I out versus V in. These don't have any specific names. We just call them normal transfer characteristics. Okay, these are just called transfer characteristics. Okay, so keep this in mind, that what is the difference between these three types of graphs. All right, we draw IV graphs for devices, waveform graphs for any particular wave, voltage or current wave that we may be supplying to a circuit, and transfer characteristics for circuits. So in this case, the transfer characteristics we drew here, this is for this circuit. Okay, so we have a rectifier circuit. Our circuit looks like this. Okay, we have some diode and some resistor. All right, so this is the box. This is the box that we are trying to find the transfer characteristics of. All right, our input port, this is our input port, and this is our output port. Okay, so compare this box to this box. All right, compare this box to this box, and you see we have and we plotted the input voltage and the output voltage. So our transfer characteristics look like this. All right, okay, so that was the review of rectifiers that we have learned until now. As you know, that these rectifiers have a simple drawback. All right, what is the drawback of these half-wave rectifiers? Well, the drawback of half-wave rectifiers is that how does a half-wave rectifier work? Why is it called a half-wave rectifier? Because for this circuit, if we supply an input voltage like this, suppose we have an input voltage like this, okay, the output of the voltage, this is again a waveform graph. I should write what type of graph I'm drawing. This is V in versus time. Okay, so this is a waveform graph. So the graph of the output voltage versus time will be V out versus time will be like this. All right. Okay, so as we can see that this circuit only corrects or rectifies, only allows to pass the positive part of the input voltage. Okay, it does not allow to pass the negative part of the input voltage. Well, we know because we are trying to make a DC signal, and a DC signal has only a single polarity. All right, so since the AC signal has two types of polarities, we are only passing the single polarity. But the drawback is you also have a voltage in the negative cycle in the input of the circuit. All right, but you are not getting any voltage of that negative part during the negative cycle of the output. Okay, the negative cycle of the output is, well, 0. I mean, there is some voltage, albeit negative. That voltage is negative, definitely. There is some voltage in the input of the negative cycle, but you don't have that negative voltage in the output. Okay, so can we make some form of a circuit that can actually use this negative voltage in our AC to DC conversion? Okay, can we make, can we use these negatives, can we use the input negative cycle? Can we use the negative cycle of the input? Okay, because there is voltage in the negative cycle, we are just not getting that voltage in the output. Okay, can we use some clever tricks to design a circuit that can use the negative voltage in our AC to DC conversion? Actually, we can. Okay, so that circuit is called a full wave rectifier. This is a half wave rectifier. It only rectifies half of the input voltage, and that circuit will rectify the full wave of the input voltage. Okay, so that will be called a full wave rectifier. So in the next lecture, we will be talking about how we design this rectifier. But before going there, just I want to clarify one thing, that in this circuit, is there any power loss during the negative cycle? Many might be thinking that since there is a voltage in the negative cycle and that voltage is not coming to the output during the negative cycle, then that there must be a voltage loss, or there must be a power loss of some sort. Is there a power loss in this circuit? I mean, is the half wave rectifier, is there any power loss in the half wave rectifier? Actually, there is no power loss in this circuit. You see why? Let me show you. Because during the negative cycle, see here, during the negative cycle, we have some voltage in the input. Okay, there is some voltage V in the input during the negative cycle. But is any current flowing through the circuit during the negative cycle? What is the value of the current here? I. Well, as you know, since this is an open circuit, the current is 0. And for any power to be supplied to the circuit, we need both voltage and current. As you might know, that the formula for power is P equals VI. Alright. The formula for power is voltage times current. There is voltage in the input, but there is no current. So actually the input is not supplying any power. So the half wave rectifier doesn't actually cause any power loss. Okay, the drawback is in the drawback of a half-wave rectifier circuit is that there is voltage in the negative cycle input, but we are not utilizing that voltage. Okay, but that does not mean that there is some sort of power loss in the circuit. Okay, so if you had any misconceptions regarding that, I'm just trying to clarify it. There is no power loss, but we are not utilizing the input voltage completely in the half-wave rectifier circuit. Okay, so in the next video we will try to make a circuit that can use both the input negative cycle and the input positive cycle. Okay, so we will try to design a full wave rectifier in the next circuit. Okay, see you then.